All right, so now we are going to switch over and start talking a little bit about bone. But first, let's do a comparison of cartilage and bone. So they are both, hold on, let me switch my pen. They both support and protect. They both have a role for supporting and protecting the inner structures of our body. The mature cells are also located in lacunae in both tissues. So both in bone and in cartilage, you are going to see cells that are located in lacunae. As I mentioned, cartilage is avascular, but this is very different from bone. Bone is highly vascular. There's quite an extensive network of blood vessels that run through bone. And then we talked about the ground substance in cartilage being firm but flexible. In contrast, bone, it is dense and hard. And there's a little bit of flexibility in living bone, but not very much. And then we also discussed how cartilage cannot grow and repair very easily. And with bone, there is actually an extensive remodeling and repair that can occur. And you can actually replace your entire skeleton every 7 years ago. And this allows your skeletal system to adjust itself based on how you use it. So the composition of bone or osseous tissue. So 1/3 of all bone is made up of organic material. So this is mostly collagen fibers and a few other types of other things like cells. And then 2/3 of it is actually inorganic, is made up of minerals. So it is mostly calcium and phosphate. So ions of calcium and ions of phosphate are stored in bone. And these are stored in the form of insoluble crystals. We're going to leave this part out for now. And then there are specialized cells that live in a matrix, just like we were talking about with all of the other types of connective tissues. And these cells, there's 4 types of cells that are going to be present that we're going to talk about. They're present in bone. So there are osteocytes. These are the mature cells. There are osteoblasts. These are going to be able to build bone. Osteoclasts, which I'll go on to show you, these have the ability to reabsorb bone. And then osteoprogenitor cells, these are like a stem cell and can give rise to these 3 other types of cells if needed. So here is another view of these specialized cells that I was referring to from the last slide. So again, these specialized cells are in a solid crystalline matrix, and there is a small volume of ground substance. So again, most of the matrix is made up of calcium salts, and there are many fibers there. So let's take a closer look at the different types of cells that you're going to see. So the osteocyte, this is the mature cell. And this cell is going to be living in the lacunae and maintaining the bone around it. The osteoblast, blast means to build. And these are cells that are actively secreting the components of the bone matrix. So when you build bone, there is a lot of osteoblast activity. And sometimes the osteogenic cells, these stem cells here, if there is a lot of activity, they will divide to give rise to new osteoblasts. And then we have this other type of cell called the osteoclast. These are relatively unique. Their job is to reabsorb matrix. So we store calcium and phosphate in bone. And sometimes we need to pull those ions back out again. And you're going to learn about the role of calcium and phosphate in physio, but the osteoclast is there to release these ions. The osteoblast and the osteoclast are only on the surface of the bone. They are never trapped in lacunae because they need to move. So the osteoclast takes away minerals and leaves the collagen fibers. And I'm going to show you a picture of that. So here is these images are really remarkable. So this is showing you that the osteoblast and the osteoclast are only on the surface of the bone because they cannot be trapped inside the lacunae. So you can see the osteoblast here living on the surface of the bone. And you can see, this is a really interesting image. You can see the osteoclast here, and it is reabsorbing the minerals and then leaving the collagen fibers behind. So this slide outlines the functions of the skeletal system. So the organ is this particular organ called bones. So bones help with support. They allow us to stand. Bone protects our internal organs. So our ribs protect the thoracic cavity. The skeletal system is involved in movement. It allows for movement, but it does so because of muscles. So the skeletal system itself cannot move, but when muscles are placed on top of the bones, that is what creates movement. The skeletal system stores minerals, like I had mentioned previously, calcium and phosphate. And then within the bone marrow, so inside the bone, there are cavities, which I'll go on to show you, and there is bone marrow within the bone, and there is where the production of all red blood cells and white blood cells occurs. So let's take a look at the structure of bone. So bone is made up of two types of osseous tissue. There is compact bone, which is also called dense bone, and there is something called spongy bone, which is also referred to as trabecular bone. And despite the name of spongy bone, it is not a sponge or movable like a sponge. It is actually very rigid. It's just very porous. Compact bone is dense and solid. It forms the walls of the bones. So the outside portion of bone, this gives bone a lot of strength. And that is where you're going to find compact bone. There is also the medullary cavity inside the middle of the bone, which contains the bone marrow. This is an image of dried bone. So all the bone marrow has been removed. And you can see the compact bone on this outside here portion of the bone. This is the very dense part of bone. And then you can see the spongy bone. It's also called cancellous bone, but we can call it spongy bone. Spongy bone is fine. And this is where it gets its name, so you can see a lot of openings and little chambers throughout spongy bone. So let's start by looking at compact bone first, and then we'll talk more about spongy bone. So the fundamental unit of compact bone is called the osteon. That is the functional unit of compact bone. And we will use a lot of osteons to build compact bone. So an osteon has layers called lamellae. And these are layers of dense osseous tissue that is surrounding a hollow chamber. And this hollow chamber here is called the central canal, sometimes referred to as the Haversian canal. and this contains blood vessels and nerves. So this is an image of a single osteon. It is a long tube of bony tissue. All right, this is a much more complex view of compact bone. So here is one bone. We're looking at one bone here. And we're actually looking at the humerus and the wall of that bone. So we are going to enlarge it by looking here. And we're looking at the outside portion of the bone. So, surrounding the bone, which we'll talk about later as well, you're going to find a periosteum. And this is similar to the perichondrium, but remember, chondro refers to cartilage. All right, and the rest of this picture is showing you compact bone. Most is made up of stacks of osteons put together, and they're running parallel to each other. So here is one osteon, here is another, and another, and another. So you can see all of these osteons running alongside of each other. And inside you will find, deeper, you will find spongy bone. So let's take a closer look here first. So we're going to take one osteon out and blow it up a little bit. So that's what we're looking at here. And you can see the cells. So there are individual cells here, right here. All of these are osteocytes. All right, so these are the cells that are living inside of the lacunae. And you can notice that the cells have lines reaching out to nearby cells. So all of these right here, they have, and they're running through little hollow tubes. And these little hollow tubes within the bone are called canaliculi. So this is like building a canal to connect one cell to another. This allows the cells to connect to each other. So these osteocytes have long processes. And again, they run through hollow channels through the bone. So you can see an individual osteocyte in its lacunae. So let me show you a close-up, and we'll come back and talk about some of these other features that you find in compact bone. So this is an amazing image. You can see an individual osteocyte. So here's the osteocyte right here, living in its lacunae, that kind of dark space right there. And you can see these processes stretching out from one cell to another. So here's like another one here through these tiny holes called canaliculi. Okay, and most of the canaliculi are missing here. You can see that some of them dip down. So there's these little holes here that they're traveling through. Okay, and these processes are very important. So only the cells closest to the blood vessels can get nutrients. The other cells have to rely on what's called these pseudopods, these arms stretching from the osteocyte. They have to depend on these to deliver nutrients. And between the pseudopods are gap junctions. So this is what's going to deliver nutrients and waste. So you can't use diffusion because it is a solid matrix. So keep in mind that osteocytes are the only cell type that can live inside the lacunae, okay? So when we talk about how bone develops and grows, we'll talk more about osteoblasts. But basically, as soon as an osteoblast becomes trapped in a lacunae, it changes into an osteocyte. So osteoblasts, osteoclasts, and osteoprogenitor cells can only exist in two locations. Okay, so here is the osteocyte living in the lacunae, and the osteoblast the osteoprogenitor cell, and the osteoclast, they only exist in two locations. They can be on the outer edge of bone in the periosteum, and they can also be in the endosteum. I don't know why that keeps doing that. The endosteum is an inner layer that surrounds the spongy bone. So they are there to grow bone, remodel bone, and repair bone. And we'll talk about that more later in the lecture. But repair is always done from the outside in. So I mentioned lamellae and how the osteon had lamellae surrounding the central canal. So there's a particular name for that. So here is one osteon, okay? And you can see the lamellae here that surround the central canal. It has a very particular name, and it is called concentric lamellae. Those are the structures that surround the central canal. And they're called concentric because they are forming concentric circles, kind of like a bullseye does. Okay, those are concentric lamellae. So there's one osteon, and you can see the central canal. You can see some of the cells living in the lacunae. Here's that central canal where you can find those arteries and veins. And the lamellae are wrapping around the central canal. The outer edge of bone, which is only going to run around the circumference of the entire bone, you're also going to see lamellae here. And because they are running around the entire circumference of the bone, they are called circumferential lamellae. These are not part of the osteon. They are only on the outer edge. Then there is a third type of lamellae that's also not part of the osteon and not on the outer edge. They're kind of here in between the osteons. These are called interstitial lamellae. And this is actually an artifact of bone remodeling and growing, which we'll talk about again at the end. So here is an actual histology image where you can see an individual osteon. You can make out the central canal, and you can see these concentric lamellae going around like this. Here is an enlarged picture of the histology. Again, you can make out these individual osteons here. You can make out the concentric lamellae. You can see the central canal. You can also see all these tiny little wiggly lines here. Those are the canaliculi. And that is the way those osteocytes can communicate with each other. All right, let's take a closer look at spongy bone. So we're talking about this area right here. Spongy bone does not have osteons. There are no osteons there. They have pieces of bone with lamellae, but no central canal. So this is kind of what they're looking like here. So instead, there are blood vessels that weave kind of in and out of that, of all of those little, like all those spaces there. They're kind of weaving in and out of there. So they get their nutrients. There's little tiny holes along the spongy bone here. and they get their nutrients from these little holes that lead to canaliculi. So none of the cells are very far from the surface, so they don't need an extensive network like an osteon. So that's what spongy bone looks like. And then in the spaces, additionally, within these spaces here, you're going to find bone marrow. And again, the bone marrow, there are cells in the bone marrow that are going to go on to produce all of the red blood cells and white blood cells of our body. This is another great representation of what spongy bone looks like. So if you cut bone in half, you can see the compact bone here on the sides. All of this is compact bone. And then here is the spongy bone. So the spongy bone make the trabeculae. That's the pattern that you see there. You can see the lamellae here, but they're not in the same pattern as you saw with compact bone where you have the osteon. And then you have these little holes here where the nutrients can then access those cells that are there, the osteocytes. There are a couple important terms that we need to define that we use for describing long bones. So and I'll show you a picture of this on the next slide, but the diaphysis of a long bone is referring to the shaft of the bone. The epiphysis is referring to the ends of the bone. And then the metaphysis is sort of like this middle area. So let's kind of go back and forth between these two slides so that you can see this. So here is the diaphysis. Again, that's the shaft of the long bone. On each end is an epiphysis. And then in the middle here is what's called the metaphysis. Okay, so those are some descriptive terms to describe long bones. It's also important to note that there is a large blood supply, so bones, always keep in mind, are well vascularized. And then there is that cavity that runs in the middle. It's a hollow cavity called the medullary cavity, and that is filled with marrow. So you can kind of see where the medullary cavity, it's going to be deep in the middle here. It's going to run through kind of the center region here. It wasn't a great drawing, but within that cavity is going to be bone marrow. Bone marrow is made up of a lot of cells and lipid, so you're going to find red blood cells and white blood cells being produced in the bone marrow. All right, so we need to touch on two other important topics for this lecture, which is bone development and growth. And there are two types of ways to grow bone or ossify. So this is two types of ossifications, two ways that bone can grow. And I'm going to talk about each of these. So the first one is called intramembranous ossification. Okay, and this is the name kind of implies how it is working because it is going to replace a membrane which is made out of mesenchyme. Okay, and I have pictures to just show you this, but there are only certain bones that use intramembranous ossification. So the only bones that are made by this method are the clavicle, the mandible, the face, the bones of the face, and the skull. Okay, there are no other bones in the body that use this type of method to make bone. The second one is endochondral ossification. So as the name would imply, so you have chondral here, we know that that means cartilage. This is going to be replacement of cartilage. So I'll show you what that looks like. There's going to be a model, like cartilage is going to make the model of all the other bones of our body. And then systematically it's going to be replaced. So the chondrocytes will be replaced by osteoblasts. So this occurs in all the other bones in our body that bear weight, the vertebral column, the long bones, etc. All right, so let's go on to talk and describe intramembranous ossification in more detail. So this is a really great picture because it's showing you photos of 10 and 16 weeks of development. So I want to talk about how the skull is formed in the face. So you can kind of see here how it starts as kind of a membrane here. And then over time, it is replaced by bone. Okay, actually, I'm going to skip this for right now. Let's just move on to intramembranous ossification. So what happens, like I said, you saw that membrane in the other picture. So you have a membrane of mesenchyme. That's where it begins. So, and you remember where mesenchyme is derived, right? From the mesoderm. So what happens is you have these mesenchymal cells, and these cells start to kind of condense in the middle. And there are blood capillaries nearby. So this is kind of step one, where you get condensation of the mesenchyme in and around blood vessels. The second thing that happens is you form what's called a primary ossification center. So what's going to happen is you're going to get an infiltrate of osteocytes and osteoblasts. So they are going to come to this region and kind of take over. So these osteoblasts, they are going to be what lays down the matrix. And they're going to lay down something called osteoid tissue. Osteoid tissue contains the fibers, like the collagen fibers needed to make bone, as well as the ground substance. So all of that's going to happen by the presence of osteocytes and osteoblasts coming into this region, and they're going to form this first area that is going to turn into bone. And then what happens is you start getting spongy bone created. So we're replacing the mesenchyme with spongy bone. You're going to get a lot of blood vessels coming into the area. You're going to get the osteocytes living in their lacunae, and this nice trabecular structure is going to form. And then over time, you're going to get some compact bone form. Spongy bone is here. Compact bone is along the sides. And you're going to continue to get this area to be vascularized, and you're going to get that nice periosteum, that protective covering around the bone on each of the sides there. So this is the method that is used to produce those facial bones, the skull, and the clavicle. And again, it starts out as a sheet of mesenchyme in the embryo, and then later turns into bone by forming first an ossification center, where you're going to get replacement of those mesenchymal cells by osteocytes and osteoblasts. Endochondral ossification is a little bit different because what it's doing is much of the early skeleton of the embryo is formed by hyaline cartilage. So hyaline cartilage is going to be the model by which bone will then be produced over, okay? So what's going to happen is that the cartilage is gradually replaced by bone through this process. So again, you're going to use cartilage as a model, and then the bone is going to grow in diameter and in length. All right, so you're going to get some appositional growth, and some interstitial growth. Let me show you what that looks like. So this happens in about 5 stages is how your textbook breaks down this process. So again, hyaline cartilage is going to be the model by which bone is then going to be produced from. So here is like a typical long bone, and again, it's going to start as hyaline cartilage. And what's going to happen, so again, hyaline cartilage is made up of chondrocytes. The chondrocytes are going to start to condense and die. So they're going to start to die here in the middle, and they're going to undergo something called programmed cell death, and they're going to leave empty lacunae. And then osteoblasts will come in and inhabit that, okay? And you're going to get another, what we call a primary ossification center when those osteoblasts come in. In addition, you're going to have cells come in on the sides of where the hyaline cartilage is and begin to form what's called a bony collar. So on the second step, you're seeing that cartilage is deteriorating and osteocytes and osteoblasts are coming in to inhabit that location. So the cartilage in the center of the diaphysis calcifies and develops cavities. That's what's happening in step 2. In step 3, what is happening is you're going to get an invasion of blood vessels into that area. And we know that blood vessels are not present in cartilage. So as soon as that cartilage starts to break down and bone cells start to emerge there, you will get an appearance of blood vessels in that area. Okay? So then what happens is we're breaking down the hyaline cartilage in the center to produce a medullary cavity. At the same time, you will start to see secondary ossification centers at each end of the bone, and the same process is going to start to happen again. So you're going to see chondrocytes die, and you're going to see osteocytes come in and osteoblasts come in. So as quickly as the hyaline cartilage is disintegrating, you are going to get bone production. And then the last step, you will leave some of the hyaline cartilage here at the ends. And this is what is going to be converted into articular cartilage. Remember, we talked about how smooth the ends of the bones look because that is how the joint is going to form. So some of that hyaline cartilage will remain at the ends. That will become articular cartilage. And then there is another important region right here. There is another region of cartilage that will remain, and this will become the epiphyseal plate. And another name for the epiphyseal plate is the growth plate. So this will be the area in which bone will grow. So as babies, bone will grow and it will become longer. So bone will be pushed, the heads of the bone will be pushed longer, and the bones will continue to grow through your teenage years and kind of stop growing as you move at the end of adolescence. And this area, this growth plate, will eventually get smaller and smaller and smaller, and that is when bone growth will cease to happen anymore. You can actually see these epiphyseal plates, so these growth plates here, on an x-ray. So you can almost determine if somebody is still growing or not. So here is a hand x-ray from, I think this is like a 10-year-old compared to an adult. And you can actually see the growth plates on all of the bones in the hand because this child is still growing. And then as we age, those growth plates disappear and we are unable to grow our bones in length anymore. So this is a summary slide of kind of what I talked about in terms of the epiphyseal plate. So in childhood and adolescence, the bones can lengthen and they can grow through at this area called the epiphyseal plate. So cartilage, that hyaline cartilage that makes up that plate, is replaced with bone tissue as quickly as it grows. So that's how bone is growing in length. And the epiphyseal plate maintains a constant thickness, and so the whole bone can grow. But towards the end of adolescence, this epiphyseal plate kind of gets thinner and thinner. Okay, so the chondrocytes in the epiphyseal plate are going to divide less and less. The plate itself becomes thinner, so the cartilage in that plate stops growing. It is then replaced by bone tissue, so you won't even be able to see it on an x-ray anymore. And then the long bones will stop lengthening when the diaphysis and the epiphysis fuse together, so you won't see that plate anymore. So let's talk about a couple different types of fractures that you've probably heard of. So a transverse fracture is when the bone is kind of cut. It's a nice line separating the two bones and kind of separates them in half. A linear fracture is a line down the bone. Oblique is a fracture on a diagonal. An oblique displaced is when the two bones kind of come apart. A spiral fracture is a twisting force. So this is very common. And usually if you end up in the ER with a spiral fracture, it will alert the staff that it is possible that child abuse has occurred. This is a common fracture from twisting motion and happens lots of times when a child is experiencing abuse. A green stick fracture, this is also interesting. This kind of occurs with kids. You can kind of think of it like if you take a stick off of a tree or a branch off of a tree and it's living and you try and kind of crack it or break it, it's green in the inside, so it kind of bends instead of breaks. That's the idea of a green stick fracture. So you get a little bit of fracturing on the edge, but it doesn't break all the way through. So that kind of happens mostly in children. And comminuted is where you get lots of fractures and small pieces of bone kind of left at that site. These are examples of green sticks, so you can see it's not a break all the way through. Transverse is when you do get a break all the way through. That's what you're seeing there. All right, so we'll finish up by talking about what the stages are of healing a bone fracture, and then we'll finish with a few disorders that happen with bone to kind of bring some clinical relevance to this. So because bone is so highly vascularized, the first thing that happens when you fracture a bone is that usually a hematoma forms. Because of all these blood vessels, you get a lot of blood leaking into that site. You get this mass or a clot called a hematoma that forms at the fracture site. This site becomes swollen, it is painful and inflamed. So that's the first stage of a fracture. The second stage is that the break is splinted by fibrocartilage callus. So this is a mass of connective tissue that kind of comes to this site to provide support. So you get this fibrous tissue, fibrocartilage, that enters and is grown in this site where there's a fracture. You're going to get blood vessels start to repair themselves and reconnect. And then you will start to turn that cartilage tissue back into bone. So you'll get what's called a bony callus. You'll get spongy bone here. It's not exactly perfectly made, so you'll get some osteoclasts that'll come in here and kind of remodel the bone, and then you'll get a healed fracture. So that is the stages of bone remodeling. And I put them all on one slide so you can see them all next to each other, and you can see the stages of bone remodeling here and how that occurs. And lastly, we'll talk about a couple diseases that are related to bone development. One of them being rickets. So rickets is a vitamin D deficiency. And you need vitamin D to absorb calcium. So we've talked about the role and how bone stores calcium and phosphate and how it creates that crystalline structure. So if you have a vitamin D deficiency, your bones are weak and they become bendy. So you get this kind of bowed appearance, especially because this is where you bear weight. And this, has been and can be an epidemic at times when we have, I think I talked about this in another part of the lecture, where if you're not getting enough sunlight because we process vitamin D in combination with UV from being outside, and, especially during COVID when we're not going outside enough, we can end up having a vitamin D deficiency. This is why milk is fortified with vitamin D as well as cereal, because it became, an issue where kids weren't playing outside nearly enough. So you get soft, weak bones, and again, this occurs in children. Osteogenesis imperfecta. This is also called brittle bone disease. This is caused by abnormal type 1 collagen synthesis. We didn't talk about the different types of collagen, so it's not that I want you to know specifically about it, but just that you understand we've talked about how important collagen is in connective tissue and in bone. So if you have a mutation or any kind of abnormality in the production or synthesis of collagen, you can imagine the damage that this would cause. The bones in these children are very, very fragile, and they are so susceptible of fractures. Just normal everyday play, walking around, bumping into things can cause bone fractures. And then lastly and we didn't really talk about this in detail yet, but there are hormones called growth hormone that is made by the pituitary gland, and this is going to modulate how much bone growth we get when we're toddlers and into adolescence. And so this has to be regulated just right. So dwarfism or achondroplasia, this is when you have a genetic reduction of this growth hormone, so the bones do not grow normal to the normal length. And then in contrast, on the opposite spectrum, if you have excess growth hormone during these critical times when you're growing bones, you will the bones will be excessively long. Okay, so those two are important in terms of regulating growth hormone at the right time during development to regulate our bone growth. All right, I'm going to wrap up this lecture. We will take a look at bone in lab as well as look at a lot of the histology that I went over.